Alright guys, in this video we are going to talk about how we calculate the pH value at equivalence points for a weak acid strong base titration. Take a look at this question. A titration of 100.0 ml of 0.100 mol per liter of methylamine, this is a weak base, with 0.250 mol per liter of nitric acid, a strong acid. Calculate the pH value at equivalence point. Kb value of this weak base is given 3.7 times 10 to the negative 4. This is the equation that I need you to understand before you start your calculation. Weak base is going to react with strong acid to generate the weak acid and the nitrate. When you reach the equivalence point, both reactants are gone and you have this weak acid left. So our target actually is the calculation a pH value from this weak acid solution. In order to do that, you need to find out the concentration of this weak acid. Okay, so that is a process. Step 1. Let's calculate the volume of nitric acid needed to reach the equivalence point, because that will help us calculate the total volume of the solution. You can use MA VA equals to MB VB to do the calculation. Because this is a 1-to-1 ratio reaction, so this equation is available for us to use. Concentration of acid 0.250 mol per liter times the VA. This is what we want to know. MB 0.100 mol per liter times VB 100.0 ml. And if you do the calculation, it tells you that VA is 40.0 ml. Alright, step 2. Stoichiometry calculation for the mole number of this weak acid at equivalence points. This is the equation that we need to use, okay, to do the calculation. Let me move this up a little bit. Okay, so remember the chart we need to use to do the stoichiometry calculation: before reaction, change, and after reaction. Before reaction, the mole number of methylamine is this. Concentration of this methylamine 0.100 mol per liter times 100 ml. Of course, you have to convert the ml to liter. Okay, 1 liter. And my calculation gives me 0.0100 mol. Nitric acid concentration is 0.250 mol per liter, and the volume is 40 ml because you need 40 ml to reach the equivalence points. Okay, times, convert that to liter. And calculation result is 0.0100 mol. And for this weak acid, before reaction, you don't have any weak acid, so it's 0. The change, because this is a 1-to-1 ratio, all of the reactants are gone, okay, when you reach the equivalence point. So the change is negative 0.0100 mol for both reactants. And then you are going to generate 0.0100 mol of this weak acid. So after reaction, both reactants are gone, and you have 0.0100 mol of this weak acid. Alright, so this is step 2. Step 3, now we know the mole number of this weak acid it's time for us to calculate the concentration of this weak acid. So step 3, concentration of this weak acid equals to the mole number of this weak acid from step 2, 0.0100 mole, divided by the volume of the solution at equivalence point. You start from 100 ml of that weak base, and you need 40 ml of the strong acid to reach the equivalence point. You add them together, that is a total volume of the solution at equivalence point. Okay, so in order to do the calculation of molarity, you convert that to liter. And my calculation is 0.07143 mole per liter. Okay, 3 significant figures. Now, based on this calculation, we can go ahead and do the calculation of the pH value by using the IC charts. Okay, here is the IC charts that we need to use. Initial concentration, change, and equilibrium concentration. This is a weak acid, so in water, it's going to dissociate to give you conjugate base and the hydronium. So initial concentration of this weak acid is from step 3, 0.07143 mole per liter, and 0, 0, and negative x, x, and x. So equilibrium concentration for all 3 species can be expressed like this. X and X. Alright, now when you look at this equation, because hydronium is one of the products, so in order to find out the value of X, you do need to use the Ka of this weak acid. How do we do it? We know the Kb for this conjugate base, so 10 to the negative 14 divided by the Kb value, and that is 3.7 times 10 to the negative 4. Okay, so my calculation gave me 2.7 times 10 to the negative 11 as the Ka value. That equals to x squared over 0.07143 minus x. Again, let's assume that x is going to be very small, so approximately that would be x squared over 0.07143 itself. Okay, so if you solve this equation to find out x is 1.389 times 10 to the negative 6 mole per liter. Alright, of course we have to double check and see if our assumption is valid or not. So 1.389 times 10 to the negative 6 mole per liter divided by the initial concentration 0.07143 mole per liter times 100%. And that is very small, 0.0019%, which is much less than 5%. So our assumption is good. We can go ahead and find out the pH value because X is this, and that is the concentration of hydronium. So if you take the negative logarithm of X, that is the pH value of this solution at equivalence points. So negative logarithm of 1.389 times 10 to the negative 6 mole per liter, and that gives me 5.86. pH value is less than 7. It tells us this is an acidic solution. And from the very beginning, when we discussed the reaction equation between the two reactants, we said the product, okay, one of the products is a weak acid, so it's supposed to give us a acidic solution, and our calculation here confirmed our prediction. So our calculation is good. This is a weak base strong acid titration. Please let me know if you have any questions.